right, welcome to a lecture covering 4.1 material over linear functions. Now I've got 27 slides to get through, so this will probably go over an hour. The good news is that the reason there's so many slides is because we're dealing with graphs and graphing, and so I had to have a lot of room. But I'll apologize for how long the notes are as well that you print out. I think it's 14, ended up being 14 pages. But let's go ahead and get moving forward on linear functions. Okay, so there are many situations that involve constant change over time. And when we're talking about constant change, that brings us into the realm of linear functions. So we've already talked about rates of change, and this should feel very familiar to you from our discussion over rates of change. So a linear function, which is defined as a function with a constant rate of change. This is a polynomial of degree 1. So x will be raised to the understood first power. You won't see written x to the first power, you'll just see x. So it's understood to be raised to the first power. There are several ways to represent a linear function, including just a sentence, a word form describing the situation, function notation, tabular form, and graphical form, and we're going to look at all of them. Okay, so suppose a maglev train travels a long distance and maintains a constant speed of 83 meters per second for a period of time once it is 250 meters away from the station. So in other words, it goes 250 meters away and then it starts booking it at 83 meters per second. How can we analyze the train's distance from the station as a function of time? So in this case, my distance, b, is going to be a function of some time that I plug in, t. Okay, so the train's distance from the station is a function of the time during which the train moves at a constant, this is what makes it linear, a constant speed plus its blank distance from the station when it began moving at a constant speed, plus its, I don't know, beginning distance. It's not really the beginning distance, it's 250 meters from the station. I can't remember what word goes in there. Plus its, I'll say extra distance from the station when it began moving at constant speed. See, that's what happens when you type up note sheets at 3 a.m. You forget what blanks you were talking about when you put a blank there. All right, so here's our situation. Remember again, speed is the rate of change. Recall that a rate of change is measured on how quickly the dependent variable changes, that's your y values, with respect to your independent variables, your x values. The rate of change for this example is constant, which means that it is the same for each input value. In other words, 10 seconds down the way, I'm still going to be traveling at 83 meters per second. 10 minutes down the tracks, I'll still be traveling at 83 meters per second. That is what it means when it says a constant rate of change. Another approach to representing linear functions is by using function notation. One example of function notation is an equation written in the slope-intercept form of a line, where X is the input value, M is your rate of change, and Y is the initial value of the dependent variable. So this is an equation written in slope-intercept form. So I have my input and output variables, that's X and Y. So X, Y is equal to my input and my output. M in this case, M is equal to my rate of change, which we will find in a moment is also known as slope. And then my B value, this represents my y-intercept. And then this is just the same equation written in function notation. Instead of writing y, I wrote f of x. And so there's no difference in those two equations. Okay, so we have our situation here again. Let me just point out the important stuff. As time increases by 1 second, so for every 1 second, the corresponding distance or output increases by 83 meters. The train began moving at this constant speed at a distance of 250 meters. In other words, before I started timing my seconds, I was already at 250 meters away from the station. So if I want to start filling out this T of T chart, at the 0th second, I was already at 250 meters. And this is when I started saying, okay, 1 second from now, I'll be 83 more meters down the road. Another second from that, I'll be 83 more meters. So this is where that constant rate of change began. So let's see, 250 plus 83. So 1 second later, I'm 333 meters away from the station. Another second later, so plus 83, I'm 416 meters away. And then another second later, I'm 499 meters away. That's fast traveling. Okay, here's a Q&A. So these are just common questions that students ask. Can the input in the previous example be any real number? So talking about the situation of time. Time being your input, miles traveled or distance from the station being your output. So the answer to that question, basically the question's asking is, do I have any domain restrictions? Well, if you think to yourself, your domain is represented by your time, then yes, you do have restrictions. You cannot input negative time values. There's no such thing as negative time. So the domain for function d of t would have to be starting at the 0th second, and then I can go through positive infinity. I can travel for as long as I'd like until the fuel runs out or whatever. But you cannot go below the 0 second. Okay. When we plot a linear function, the graph always plots as a line. a line has a constant slope. So let me just give you something to look at. Here's a line. So the slant or the slope of this line is the same from here to here as it is from here to here, as it is from here to here. So the slope of a line is constant. In other words, the rate of change of a linear function is constant. So it's always going to graph as a line. That's why we call it a linear function. You could look at that as linear. So, and that determines the slant or the slope of the line. The point at which the input value is 0, so on my little sketch graph, we'd be talking about this point here, that's an x value of 0. When you have an x value of 0, what you're actually finding is the y-intercept of the line. We can see from the graph, which I don't have it graphed here yet. They had it graphed in your book, and I took the graph off because I wanted to put our own information onto the graph. Let's go ahead and bring that table over here and put it onto the graph. Okay. All right, so I have the point 0 to 50. 0 to 50, about right here. And then 1, 333 is about right here. And I'm just eyeballing my y values. 2, 416 is about right here. And 3, 499 is about right here. And you can see, because there was that constant rate of change of 83 meters per second, 83 meters per second, 83 meters per second, I end up getting a line. So the slope or the rate of change of a line is constant. And what it points out here is, notice that the 0 to 50, this represents the distance of the train from the station before we began moving at that constant speed. So this is before we began counting, because it took them a little bit of time to get up to their speed. So basically it took them 250 meters to begin traveling at that 83 meter per second rate. Oh, let's look at what I have at the bottom. The speed is the rate of change. Recall that the rate of change is a measure of how quickly the dependent variable changes with respect to the independent variable. So in this particular case, and your dependent is your y value. So what's happening here is that I'm changing 83 meters for every 1 second. So I would write that as 83 meters over every 1 second that I travel. In this case, my slope is going to be 83 over 1, which we would just write as 83. Okay, a linear function is a function whose graph is a line. Linear functions can be written in slope-intercept form, and this is slope-intercept form right here. F of x equals mx plus b. Notice the slope is always the coefficient on the x term. or I could, instead of saying the X term, I could say the input term in case we're not using X and Y. So whatever's on your X-axis, your horizontal axis, whatever variable is there, that is the variable that the slope is going to attach to as its coefficient. And then the rest of this just shows that your y-intercept is b, so I'll just point that out here. And a y-intercept always comes in the form of 0 for your x value and then some y output value. Okay, so the pressure P in pounds per square inch, which is PSI, that's how your tires are measured, I know that. On the diver in the figure, and I didn't include the picture because it was full color and I didn't want you to have to print out a full color picture when you print the notes out. So, depends upon her depth below. Okay, so P pounds per square inch depends on, so P is your output and it's depending on depth below the water surface D in feet. So notice you have your input variable here, depth, and that gives you your output variable of PSI. So it just says to restate this function in words, and it wants you to use the equation and basically describe what this equation is telling you. So I would say that this equation is telling me that the PSI, or the pressure per square inch on a diver. Okay, so all I've done, and I'll color code this. Let me take all this off. Okay. So this part of my statement is describing my output variable. So the PSI on a diver is another word for equals. Is what? Okay, so my slope or my rate of change is 0.434. And don't forget that my rate of change or my slope is always given as change in output over change in input. So in this case, my output is PSI and my input is depth in feet. So what that 0.434 says is the PSI on a diver is changing, because it's a rate of change, it's changing at 0.434 PSI per every foot of depth. But it's depth after 14.696 feet. So let me finish color coding this. Changing at 4.34 PSI per every PSI. Let's see, so that's 4.34 psi, and that is per every foot of depth, and we don't start getting that rate of change of psi until 14.696 feet. Okay, so hopefully that helps you understand how to break those equations down. Okay, so slope in general, the slope of a line, and I took this from an old section that we actually don't cover in this class. This is considered prerequisite material, but I pulled it up here for you to take a look at as a refresher. So the slope of a line M represents the change in Y, so we could write this formula as delta Y, because we know delta just means change in, over the change in X. And change in means we subtract. It's a difference of position. Given 2 points, you have to have 2 points to be able to figure out the slope of a line. Following formula determines it. So if you are given 2 points, x1, y1, x2, y2, to figure out the slope, you subtract the y values. Now notice that says y2 minus y1. Since I started with my second point in my numerator, I have to start with the second point in the denominator. So that's x2 minus x1 in the denominator. So this is the formula for deciding how much change has occurred vertically and horizontally between two positions on a function. Okay, so determine whether a linear function is increasing, decreasing, or constant. So we've already looked at these characteristics of functions of increasing, decreasing, and constant. A linear function may be increasing, decreasing, or constant. For an increasing function, as with the train example, so it was increasing 83 meters every second. The output value increases as the input value increases. The graph of an increasing function has an uphill slope. So take a look at this first diagram in the center here. As my horizontal variable increases into positive infinity, my vertical variable also increases into positive infinity. And it makes this thing look like it's going uphill. So that is an increasing, also known as, it's an increasing function known as positive slope. Okay, a line with a positive slope, the graph of an increasing function has an uphill slope. Oh, I'm sorry, that blank should have been has a positive slope, and it increases uphill. Okay. Has a positive slope. A line with a positive slope slants uphill from left to right. Okay, so for a decreasing function, the slope slants negatively or downhill from left to right. For a decreasing function, the slope is negative. The output value decreases as the input value increases. So as I move to the more positive side of my x values, I'm actually moving down in my y values. So a line with a negative slope slants downhill from left to right. And if the function's constant, it's a plateau. It's a horizontal line. So that next little general note is just symbolizing and summarizing all of that information about positive and, let me write this. This is negative slope. Okay, so some recent studies suggest that a teenager sends an average of 60 texts, that should say text, not test, texts per day. For each of the following scenarios, find the linear function that describes the relationship between the input and output value. Then determine whether the graph of the function is increasing, decreasing, or constant. Okay, so the total number of texts a teen sends is considered a function of time in days. So let's just sketch a picture of that. So we have two axes here. And they are telling us that the total number, so total text, is our Y variable, or output variable, our dependent variable, and our independent variable is time in days. And it says the input is the number of days and the output. Okay, so as time moves on, I would say they're going to be sending more text. So this would have to be an increasing function. All right, B. A teen has a limit of 500 texts per month on his or her data plan. The input is the number of days, and the output is the total text remaining. Okay, so at the 0th day, that y-intercept, at the 0th day, she had 500 texts left that she could send for the month. As the days go on, she's going to be sending texts, so she's going to have less and less and less text left to send. So this is a decreasing function. My first one has positive slope. My second one has negative slope. I bet you can guess what C is going to have. A teen, it should say teen, not team, has an unlimited number of texts in his or her data plan, and it costs $50 per month. The input is the number of days, and the output is the cost for texting. Well, it doesn't matter if she sends one text or 1,000 texts. It's always going to cost her $50. So this is a constant function. Okay, interpreting slope as a rate of change. We have the change in output, also known as your rise, divided by the change in your input, also known as your run. So delta y over delta x. So remember, the thing that we have to be careful of is we have to make sure if we start with the second point in the numerator and subtract the first, we have to start with the second point in the denominator and subtract the first to get a proper value for our slope. Are the units for slope always, and I'm reading in the Q&A box there on the right, are the units for slope always the output over the input? Yes. Think of the units as change of output value for each unit of change of input value. Okay? How do we do this? If you have to be given 2 points. You name your points, point 1 and point 2, so you've got x1, y1, x2, y2. Plug them into the formula, y2 minus y1 over x2 minus x1, and that is your slope. If f of x is a linear function and the points 3, -2, and 8, 1 are points on that line, find the slope. Is the function increasing or decreasing? Okay, so first thing I'm going to do is name my points so I don't get confused. I'll call this one x1, y1, x2, y2. And it doesn't matter which one you call the first point and which one you call the second. So, I start out with the slope. Nickel's worth of free advice: whenever you use a formula, write it down. Then you don't have to spend time memorizing it. You'll just know it when the time comes. Okay, so y2 is 1 minus, remember I'm finding the difference in position, minus -2, y1, divided by x2, which is 8, minus 3. Well, minus a negative in the numerator is really plus. So I end up with a slope of 3/5. What this says is for every 5 units in the positive direction, I move 3 units up to get to another point on the line. So real quick, in case you don't remember, you've got positive and negative values that are possible for your x and your y input. So it's always your change in y over your change in x for slopes. This is slope we're talking about. And you could have a potential of being positive or negative with each other. So positive y tells you to move up, negative y down, positive x right, negative x left. So moving up 3 and right 5. Okay, so sorry, I had to pause the recording for a moment, but I'm back now. So what I was talking about is that a slope of moving up 3 units and right 5 units is the same exact thing as moving down 3 units and left 5 units, because when you divide a negative by a negative, you get a positive value. This is also considered a positive slope, so this is increasing. So when you have a positive slope, you should expect to get a positive value when you calculate it. Same thing with negative slope. When you have a negative slope, you should expect to get a negative value out. All right, so let's look at the population here. The population of a small town increased from 1442 to 1868 between 2009 and 2012. So that's setting up your 2 points right there. You have time. Time is always your input. So I have in 2009, my population was 1442. In 2012, my population was 1868. And we're asked to find the change of population per year if we assume the change was constant from 2009 to 2012. So we want to find the slope. Okay, so let me label my points here. We'll call this one Y2 or X2, Y2, and this one will be X1, Y1. It does not matter. You just can't mix up your points like X1, Y2, but you'd never do that anyway. All right, so 1442 minus 1868 over 2009 minus 2012. Okay, let me grab my calculator. 1442 minus 1868 is negative 426. Don't forget they said that this was increasing. But 2009 minus 2012 is negative 3. So here's the situation where it looks like it's going to be decreasing, but it's not. Because a negative divided by a negative is a positive. So this is 426 over 3. What this says is every 3 years, 426 people are added to the population. But they asked us to find out per year. So we need to divide here. 426 divided by 3. That leaves me 142 over 1, which is just 142. This says the population increases, because it's a positive value, increases 142 people per year. Okay, so writing and interpreting an equation for a linear function. So on the screen here you have two different forms of a linear equation. The first one is called point slope form. And actually, let me go ahead and start color coding this. So point slope form is called point slope form because what shows up in the form is an x1, y1, a given point, x1, y1, is a given point, and you have to have the slope. Now that other x and y, this x and y, this is the xy that stays. It generates your table for you, your table of values. So it generates your xy table, the points on the line. So those are going to remain there. And the last thing I'll point out about this form is you have differences here and here. So subtraction is in the form there. And that slope is the same slope we just learned. So that slope is y2 minus y1 over x2 minus x1. All right. We also have slope-intercept form, which we've already looked at. And I'm going to color code it as well. This f of x is the same thing as y, and this x is the same x as above. So this x and f of x stay to generate points. And the m is the same m as above. This is slope. y2 minus y1 over x2 minus x1. And b, we've already discussed this, shows up as your y-intercept. Which, don't forget, that's always 0 for x and then some y value for the coordinates of that point. So what I wanted to do is just take a couple points. I'm just going to make these points up, and I'm going to show you how to take something from having 2 points, put it into point-slope form, and from point-slope form move to slope-intercept form of the equation. So let's take the points 1, 3, and 4, let's see. I want to make sure that the numbers come out nice and neat, so I'm thinking here. So 1, 3, 2, 4. Let's do 4, 12. Okay, so for either of these forms of the equation, you have to have the slope. So that's what I'm going to figure out first. All right, so I have y2 minus y1 over x2 minus x1. 12 minus 3 is 9. 4 minus 1 is 3. So this is a 3 over 1. So this is a positive slope. It's increasing. I'm going up 3 for every 1 unit I move to the right. And now I'm ready to input my values into point slope form. So point slope is y minus y1 equals m times x minus x1. And x1, y1 is a given point. I can choose either point to work with. It doesn't matter. I'll choose the smaller values just to keep it a little easier to manage. So that's y minus, I don't write y1, I write my given y value, 3, equals, I don't write m because I now have a value for m, which is 3 over 1, or I can just write 3, times x minus, I'm not going to write x1, I'm going to write 1 as my x coordinate. And then this is actually point slope form. So I'm done with point slope form. But what I can do now is move from point slope form and rearrange this same equation into slope intercept form. So to do that, I need to distribute my 3, and that gives me y minus 3 equals 3x minus 3. Add 3 to both sides. And I end up with y equals 3x. I could say plus 0, but you're never going to see plus 0 written. It's understood to be there. So my y-intercept is 0. It goes through the origin. So the form of this equation you're going to see is y equals 3x. So there's my slope-intercept form. This is my point-slope form. And I got all of that. These are all the same line. Got all of that from 2 points that I was given. Okay, given the graph of a linear function, write an equation to represent the function. So how do I do that? Identify 2 points on the line. Remember, we got to start with the 2 points so that we can figure out what the slope is. So these 2 points are what you're going to use to get your slope. And that's the next step. Use the 2 points to calculate your slope. Determine where the line crosses the y-axis. That's your y-intercept. And substitute the slope and the y-intercept to write the equation of the line. And they want us to write point slope and slope-intercept form of the line. Okay, so my 2 points that I'm given are the points 0, 7, and 4, 4. We know we should expect a negative slope because I am going downhill. M equals y2, 4, minus 7 over x2, 4, minus 0. So this is negative 3 over 4. So that's down 3, right 4. Watch this. If I start at a point on the line and move down 3 and then move right 4, I hit another point on the line. So that's what slope is showing you. That's what it's telling you. How do I move to get to another point on the line? So there's my slope. My slope is negative 3/4. And I can choose either point I want to work with. I'm going to choose 0, 7. 0, 7 is the y-intercept in this case because you always have a y-intercept when you've plugged in 0 for x. But I like using 0 because it gets rid of a lot of things. So let's go ahead and look at the point slope version of this equation. Point slope is y minus y1 equals m times x minus x1. And so I have y minus y1 equals m times x minus x1, 0. Okay. So as point slope, you would want to simplify your point slope version. I think this is what WebAssign will want you to do. You may want to try it both ways. I think they'll want you to not put minus 0, but I may be wrong about that. Both of those are correct. They're the same thing. So one of those, check in WebAssign and somebody let me know. Both of those are considered correct and could be potential point slope form. Now moving from point slope into slope intercept. Slope intercept is y equals mx plus b. So I start with y minus 7 equals 3/4 x. All I need to do is add 7 to both sides. And notice we said 7 was our y-intercept. And here we are, y equals negative 3/4 x plus 7. It's sitting in the position of the y-intercept there. Let me just box this in, showing there's a valid slope-intercept form. Okay, suppose Ben starts a company in which he incurs a fixed cost of $12.50 per month for overhead, which includes his office rent. His production costs are $37.50 per item. Write a linear function C where C of x is cost for x items produced in a given month. Okay, so I'm trying to write an equation where all the points in it are going to look like x C of X. And X is items produced, and C of X is cost, total cost. Okay, so what I know I need to do, it doesn't matter how many items I produce, I have to pay my $12.50, I guess it's rent. I have to pay that no matter how many items I produce. So when I've produced 0 items, I have already started at owing $1,250. So C of X is equal to, all right, I need to know what my slope is. The slope is always my coefficient on my input value. Well, right here, I'm told how much I change in cost per every 1 item, and X is standing for items. So my slope is 37.5 or 37.50, and I multiply that by every item I produce. There is the equation that models that situation that says my total cost is gotten by multiplying however many items I produce times 37.50, and then I have to add on my $12.50 overhead, which covers my rent or whatever. All right, looking down at the bottom, same type of question, different way of giving the material. So if f of x is a linear function, f of 2 equals 11. F of 2 equals negative 11 is the same exact thing as saying the point 2 negative 11 exists on the function. And f of 4 is equal to negative 25. That's like saying the point 4 negative 25 lives on the function. Write an equation for function in slope-intercept form. So I need to start with my slope, y2 minus y1 minus negative 11, remember that's going to be plus, over x2 minus x1, so negative 25 plus positive 11. Okay, so 25 and negative 11, 14, so negative 14 over positive 2, which reduces to negative 7 over 1. So I'm going down 7 units for every 1 unit I move right. So this is a negative slope we're dealing with here. It's a negative value. Okay, I start by plugging this into my point slope form. So y minus, well, I need to decide what point I want to use. And I'll use the one with the lower numbers, so I'll use 2 negative 11. So y minus negative 11 equals m, which is negative 7, times x minus x1, which is 2. All right, now I just rearrange until I'm in slope-intercept form. So minus the negative is plus, and I'll distribute that negative 7. So y plus 11 equals negative 7x plus 14, subtract 11. And I get y is negative 7x plus 3. So my y-intercept is 3, my slope is negative 7. Okay, modeling real-world problems. We do it the same way. Working as an insurance salesperson, Aya earns a base salary plus commission on each new policy. Therefore, Aya's weekly income, so I is equal to weekly income depends on, so this is my dependent variable, so I should expect that to be my output variable, depends on the number of new policies N. The number of new policies. So don't forget, he or she, let's see, he gets a base salary. So no matter if he sells no policies or 100 policies, he gets a base salary. And so we're told last week he sold 3 new policies. Let me get a different color here. 3 new policies and earned $760. The week before he sold 5 new policies and earned $920. There are your 2 points right there. So let me just finish this off. That's NI. So to note my 2 points, I have 3, 760 and 5, 920. I do the same exact thing I've been doing the entire time. I find my slope, 920 minus 760 over 5 minus 3, and 920 minus 760 is 160, and that's divided by 2, which is 80 over 1, or just 80. So my slope is 80. I start with point slope form. Y minus, I'm going to choose one of the points. This time I'll choose the higher numbers, just to be different. So y minus 920. Oh, let me not use y and x. Let me use n and I to be consistent. So my y value is actually my I value in this problem. So that should be I minus 920 equals M, which in this case is 80, times N minus my N value, which is 5 in this case. So there's my point slope form, and I want to move to slope intercept form. Slope intercept form forms the nicest form to have your lines, the equations of your lines in. Okay, so I need to distribute. I've got I minus 920 equals 80 N minus 400. Add 920 to both sides. And I get I equal to 80 N plus 520. So let me point out what all of this means. My slope of 80. This means I earn $80 for every 1 policy sold. My y-intercept of 520, think about what a y-intercept means. It means when you plugged in 0 for your input value. So when I sold no policies, I get a base salary of $520 per week. Okay, use the table to write a linear equation. For the sake of time, because I'm barely halfway through my slides, we will just look at this last one here, because they're both tables. They're just different situations to look at. Same work, though. New plant food was introduced to a young tree to test its effect on the height of the tree. The table shows the height of the tree in feet X months since the measurements began, right? A linear function, h of x equals mx plus b is what I'm trying to write, where x is the number of months since the start of the experiment. So once again, I need to find the slope. I need to choose which 2 points I'm going to use to find this slope. I'll use these 2 middle points. So I have y2 minus y1 over x2 minus x1. And that's 1 over 2, which is 0.5 if you want it as a decimal. Or you can leave it as 1/2. Same thing. All right, I am ready to plug into point slope form, and I will choose even a different point. Let's see, I'll choose the 816.5 to plug in. It doesn't matter because you're told they're all on the line. They're all part of the data. So h of x minus, so that's y minus y1, and in this case, I'm going to have my y value be 16.5 equals 0.5. I'm definitely going to have to use my calculator on this. I am no good at decimals in my head. Times x minus x1, which is 8. Okay. Now I'm ready to distribute here and here. And that gives me h of x minus 16.5 equals 0.5x, and then 0.5 times negative 8, so this is half of 8, is negative 4. Add 16.5 to both sides. And I get h of x is equal to 0.5x plus 12.5. There's your equation. Okay, how to graph a linear function by plotting points. In other words, you're going to just create an f of x table here. So x, f of x. Just going to choose 5 input values. And I'm going to choose these wisely because I'm multiplying by a fraction that has a 4 in the denominator. If I choose to plug in multiples of 4, then these will come out to be integers. So I'm going to choose to plug in negative 8, negative 4, 0, 4, and 8. And I'll show you what I mean. I'll work out f of negative 8 for you so you can see why I chose those. This is negative 3/4 times negative 8, and I'm going to put it over 1. When I'm working with fractions, I like everything to look fractiony. Plus 6. Okay, here's why I did that. Because I can now go back and say, well, 4 goes into 4 one time and into 8 twice. And now all I have are 1s in my denominator. So negative 3 times 2 is negative 6. Plus 6 is 0. So that's 0. All right, so I'm going to do the rest of them in my head. Negative 3/4 times negative 4. Ooh, no, I'm sorry. Go back to this one. That's a negative times a negative. So that's positive 6. which gives me 12. Sorry about that. Okay. Negative 3/4 times negative 4 is positive 3. Positive 3 plus 6 is positive 9. Negative 3/4 times 0 is 0 plus 6 is 6. Negative 3/4 times 4 is negative 3 plus 6 is 3. And negative 3/4 times 8 is negative 6. Negative 6 plus 6 is 0. Okay, I'm ready to put this onto my graph. Negative 8, 0. Oh, no, 12, I'm sorry. I forgot to change it in my table. This is 12. There we go. Negative 8, 12 is actually off of our graph, so it's somewhere up around in here. All right, negative 4, 9. All right here. 0, 6. 4, 3. And 8, 0. That's it. Okay, so how to graph a function if it's given to you, graph the line if it's given to you in slope-intercept form. It makes it easier to graph when it's in slope-intercept form. All you have to do is identify the slope, which is negative 2/3, sitting right there as the coefficient on the x term, and the y-intercept, which in this case is positive 5. Okay, so you know the y-intercept is a point on the y-axis. So I'm going to go ahead and plot that point on the y-axis, and then I move from that y-intercept how the slope tells me to. So once again, here's a quick reminder of how to move with your slope. You always have y, change in y over change in x, and you can have positive and negative of each of those. Positive y up, negative y down, positive x right, negative x left. So from my y-intercept, I move down 2 units and right 3. 1, 2, 3. I know that when I move that slope, I've hit another point on the line. And then you only have to have 2 points to determine a line, so I'm ready to graph. Easiest way to graph is when you have a line in slope-intercept form. Okay, so graphing using transformations. Now I know these values are very hard to see, and I apologize about that. But when I have a line in its toolkit form, I'm going to highlight the toolkit form. This actually says f of x equal to x. That's y equals x. That's the identity line. I have a slope of 1. I go through the origin. So if I were going to expand this out so you could see all the parts of slope-intercept form, that would be f of x equals 1 over 1x. It's understood to be there plus 0. So I go through the origin and I move up 1, right 1, put a point. Up 1, right 1, up 1, right 1, and you can see it's moving unit by unit there. That is your identity line. So that's your toolkit function. That's the one you move from. And just like we learned in the last module material, when I want to vertically stretch or compress, that shows up as the coefficient on my x value. So that's your slope. So I'm not going to beat a dead horse here. I'm just going to point out, okay, I've been stretched vertically because this one is f of x equals 2x. And look, it's more vertical than the 1 over 1, our toolkit function. And then we've got one that's even stretched more vertically. This is 3x. So it's even more vertical there. And it's positive, so it's going uphill. So we've already been through all these transformations. I'm not going to dig down into this, but this should make complete sense to you. Vertical shifting, notice I've got the same slant, if you will, of the line, the same slope. And just to show you, this is f of x equals x there, right here. I have not changed the slope here. This one's f of x equals x minus 2. The coefficient on the x term is still understood 1, but what I've changed is I've shifted down 2 units. So it goes through the point, instead of going through the origin, it goes through the point 0, negative 2. So it shows up as my y-intercept right there. And I could do the same thing with all those others. Okay, so it says graph the graph using transformations. So my regular toolkit line is f of x equals x. And remember, if we're graphing using transformations, we should show this in tables. And I have x and then f of x. And I'll show negative 2, negative 1, 0, 1, and 2. For f of x equals x, my toolkit function, it says whatever you plug in, that's what you get out. Let me go ahead and graph this one on the graph so we can comparatively shift from there. So negative 2, negative 2, negative 1, negative 1, 0, 0, 1, 1, 2, 2. So I get this oblique line or diagonal line coming through just like that. That's my toolkit one, the identity. Now, my new function says, well, I'm going to compress by 1/2 in the vertical direction, and then I'm going to shift down 3 in all my y values. So, x, f of x here. The first thing I have to do is show my compression of my x values. So what I'm going to do is I'm going to multiply every single one of my original x values from my toolkit function by that 1/2. So every single one of them gets multiplied by 1/2. And I'm multiplying by what I originally started with, negative 2, negative 1, 0, 1, and 2. And that leaves me with, this is negative 1, half of negative 2 is negative 1, half of negative 1 is negative 0.5, or negative 1/2. Half of 0 is 0, half of 1 is 0.5, and half of 2 is 1. So those are my new x values. My new y values shift down 3. So I start with down 3. So I start with my y values from my toolkit, -2, -1, 0, 1, and 2. And I shift, so I subtract 3, down 3, down 3, down 3, down 3, down 3. And what I end up with there is -5, -4, -3, -2, and -1. So my new function is -1, -5. And I'm going to skip the halvesies points. No, I won't. I'll show you how to do it. -1/2, -4. So I go halfway between 0 and -1 and go down to -4. 0, -3. Half -2. And 1, -1. So here's my new no, that's a slope of 2. Scratch that crap. I should have multiplied all these by 2 because this is actually an inside inverse. I'm so sorry about that. What? I didn't do that either. So it's not 1/2. It should be 2 that I multiply all those by. And the way I knew that wasn't right is because a slope of 1/2 means I go up 1 and right 2, so it should have been less of a slant, and it was actually more vertical, so that's how I caught my mistake. These should all be multiplied by 2, not 1/2, because it's inside inverse. Doesn't look like inside inverse, but it is. I got tripped. Okay, so what that makes my outputs in my X column, our Y values are cool. It's just our X. So 2 times -2 is -4. 2 times -1 is -1. Sorry, I'm having to do pencil magic here with changing colors and deleting old values. And I apologize about that. Like I said, I'm running on Nancy after being up so early this morning. 2 times 1 is 2, and 2 times 2 is 4. Okay, now let's put this on the graph. 4, -5. 1, 2, 3, 4. 1, 2, 3, 4, 5. This doesn't look right either. My goodness. 2 times -1 is -2. Oh, that was supposed to be -4. That's why it doesn't look right. I was about to say, oh God, this is terrible. I can't edit these videos done in Collaborate. So let's see, -4, -5 right here. Now we're talking. -2, -4. Now we're right. Sorry about that hiccup. 0, -3. 2, -2. You know, the moral of the story is just put it in slope-intercept form and graph it that way. That is the easiest way to graph. There's really no need to make it more complicated than that when you're dealing with lines. And I'll just point out, once again, the way I knew I was wrong with the first time I graphed is because I have a slope of 1/2, which means to go from one point to another, I should be able to go up 1 unit and right 2 and hit the line. There we go. Okay, this says use transformations. I'm going to use slope-intercept form. So it's not in slope-intercept form, f of x equals 4 plus 2x, but to get it there, you just flip-flop those terms on the right-hand side. F of x equals 2x plus 4. My slope is 2, and I'll put that 2 over 1, and my y-intercept is 4. So plot your y-intercept, move from your y-intercept up to right 1 and put a point. 2 points determine a line, graph your line. Much nicer than transformations, huh? Okay, write the equation for a function from the graph of a line. So they've given you 4 lines on the graph, and you're just supposed to match the equation. So this is just getting you warmed up to the idea. So the first thing you'll want to do is identify the y-intercept, because you know that's what's going to be hanging on to the end there as a constant. Choose 2 points to determine your slope, and then substitute the y-intercept in the slope and slope-intercept formula line. All right, so we know that 3 of our lines have a y-intercept of 3. I've got one with a y-intercept of 3 that has a negative slope. So this line right here, I can go ahead and pick that out because I only have one that goes through 3 that has a negative slope. So let's see. That would be C. C is going to be line 4. And there's the Roman numeral right there. All right, I also have another one that's pretty easy. I have one that's got a y-intercept of negative 3. There's only one, and that's line 3. And so you can see right here, I have a y-intercept of negative 3, so that's line 3. Oh, and by the way, I knew that other one was C because of the negative 2 sitting in the position of the slope there. All right, so now I just need to decide between, let's see, line 1. So that's either a slope of 1/2, or I also have line 2. Let's see, trying to match the color, with a potential slope of either 1/2 or 2. 1/2 is going to be less sloped, less vertical, if you will, than 2. So judging on that, my orange line over here has got to be the one with a slope of 2, and my light blue line is the slope of 1/2. So this is line 1 because I have a slope of 2, and this is line 2 because I have a slope of 1/2. It's less inclined. Okay, a note on the x-intercept. The x-intercept of a function is the value of x when y, or f of x, is 0. It can be solved by plugging in 0 for y and then solving for x. So this is what that looks like. 0 equals 1/4 x minus 4. I'm going to add 4 to both sides. And that leaves me with 4 equals 1/4 x. And to get that 1/4 off of there, I multiply by the reciprocal, which is 4 over 1, or just 4 on both sides, because those divide out. And I'm left with an x-intercept of 16. Okay, so that's the point 16, 0. That's where the graph crosses the x-axis. Your y-intercept is hanging out right there. So your y-intercept is actually -4. So a quick sketch of your line says, well, I go through -4 and I go through 16. There's 2 points. I've determined my line. Okay? And we're also asked to find the x-intercept again. So I need to plug in 0 for y to find an x-intercept. 1/2 x minus 3. Add 3 to both sides. 3 equals 1/2 x. Multiply both sides by 2. And multiplying by the reciprocal to get it off of the x there. And 6 is x. That's the point 6, 0. And this is my x-intercept. And my y-intercept gotten from the equation is -3. That's the point 0, -3. Okay, horizontal and vertical lines. I promise we're nearing the end of this lesson. I've got about 4 slides left. There are 2 special cases of lines on a graph, a horizontal line and a vertical line. A horizontal line indicates a constant output. In other words, f of x, my output value, is always going to be the same thing. So if you take a look at this first graph on the left-hand side, notice my output value is always 2, no matter what I put in for x. So I've got -4, 2, -2, 2, 0, 2, 2, 2, 4, 2. That creates a horizontal line when you have a constant output. And so if you have a line that's on a graph, let's say my horizontal line was here. I can write the equation of that line because I know it goes through the y-axis at -4, so that's f of x equals -4. I have an output that is constant at -4. Okay, moving to the vertical line. A vertical line indicates constant input. So my x value always stays the same. So notice here, when I plug in 2, I get out -4. But when I plug in 2 here, I get out -2. This thing's not a function. A vertical line fails the vertical line test miserably because it is a vertical line. So these are the points: -2, -4, -2, -2. I'm sorry, 2, -2, 2, 4, 2, -4, 2, 0, 2, 2, 2, 4. And it creates a vertical line when you have a constant input. So let me just give you another example to look at. Let's say I have a vertical line here going through -1 on the x-axis. The equation of that line is x equals -1. It's my input that is constant. Write the equation of each of the lines. This is going to take 2 seconds, literally. I'm going through -4 on the y-axis. This is f of x equals -4. My output is constant. On this next one, I am moving through +7, it looks like, on the x-axis. My input is constant. I have an x of 7. Those are the equations of those lines. if two lines are parallel, now we're moving into parallel and perpendicular, they will never intersect. They have exactly the same steepness or slope, so which means their slopes are identical. And think about it. If the slopes were different, they would eventually cross and they'd cease to be parallel. So to have parallel lines, they have to have the same slope so that they'll never intersect. The only difference in parallel lines is where they cross the y-intercept. So shifted vertically away or towards each other. Perpendicular lines, well, you can see that they don't have the same slope, but one thing that we end up discovering about the slopes of perpendicular lines is that they are what we call opposite, and that's talking about the signs. Notice my orange line is a negative slope and my blue line's positive. They are opposite reciprocals. And reciprocals we usually know as being flipped. Now that's not the definition, but that's how we remember what reciprocals are. So for example, let's see. It looks like the slope of my blue line has me going up 1, 2, 3, 4, 5, and right 1. So my blue line slope here is 5/1. I should expect my orange line to have a slope of 1/5. Let me give that a check because negative 1/5. I know that my orange line slope has got to be negative because it's going downhill. And let's see if I can identify a point. It looks like it goes through the point -4, 1. So I go down 1, right 1, 2, 3, 4, 5, and sure enough, I hit a point on the line. So -1/5. These values are considered opposite, that's their signs being opposite, reciprocals, flipped. So perpendicular line slopes are opposite reciprocals. Parallel lines have the same slope. Okay, two lines are parallel if they do not intersect. The slopes of the lines are the same. So I'm going to have some line and some line that's parallel to it, and the slopes are going to equal each other. Perpendicular, I'm going to have a line, and I'm going to have a line that's parallel to it. When you multiply opposite reciprocals, you get -1. So my perpendicular slope is equal to the opposite reciprocal of my first slope. That's all that's saying to you. Okay, so down at the bottom, it says, identify the functions whose graphs are a pair of parallel lines and the ones that are perpendicular. Well, if I have the same slopes, I'm parallel. If my slopes are opposite signs and reciprocals, then I'm perpendicular. Here, my first slope, my M1 is 1/2, and my M2 is -2 over understood 1. And my parallel line slopes, my M1 is 2, and my M2 is 2. Last slide. Last slide here, thank goodness. Given the function h of x equals 2x minus 4, write an equation for the line passing through 0, 0. So that's the origin. That's also going to be your y-intercept that is parallel to h of x and perpendicular. Well, the slope that I'm starting with is 2. So my parallel slope, and that's just a little symbol for parallel there, my parallel slope has got to be 2 as well. My y-intercept is 0. My perpendicular slope, and here's the little sign for perpendicular, has got to be the opposite sign and it's flipped. So my parallel line equation, y equals, so let me use h of x just to be consistent. H of x equal to 2x plus 0. You will see this written as h of x equals 2x. My perpendicular line, h of x equals negative 1/2 x plus 0, and you'll see this written, h of x equals negative 1/2 x. All right, last problem, finally. A line passes through 2 points. Find the equation of a perpendicular line that passes through this point. So I've got to use my 2 points of my line there to find the slope to figure out how I can be perpendicular to that slope. So my first slope, negative 3 minus negative 15 over 2 minus negative 2. Those minus negatives are pluses. Negative 3 plus 15 is 12. 2 plus 2 is 4. This is a slope of 3. 3 over 1, which is just 3. So my perpendicular slope is going to be the opposite sign and flipped, negative 1/3. And now I can use the information that I need to pass through this point 6,4. So I'm just going to go from point slope, because I've got a point, and I've got my slope now, to write the equation of the line in slope-intercept form. So I start out with y minus y1 equals m times x minus x1. So it's just kind of putting everything together that we've done. Y minus y1 is 4 equals m, which is negative 1/3, times x minus 6. And I need to distribute here. So far, I have y minus 4 equals negative 1/3 x. Negative times a negative is a positive, and 1/3 of 6 is 2. So positive 2. And then add 4 to both sides. And I end up with the equation of my line going through the point 6,4 perpendicular to the line given by the other 2 points is y equals negative 1/3 x plus 6. That's all I got for you.